Okay, can you see my slides? Let me put them in presentation mode here.
Yes, we can.
Okay,
Thank you.
thanks for the introduction. I'm going to step back a little bit and talk about some of the strategic cybersecurity threats to manufacturing in general. There's many sectors, manufacturing and otherwise, that can show as examples for what we're going to face with these strategic threats so that you can try to translate them to some of the unique systems and unique consequences that we're going to find in the bio cybersecurity arena. And I think that Charles may touch on some things relating back to those areas. So first off, CyMani, the Cyber Manufacturing Innovation Institute, is one of the half a dozen and a half manufacturing innovation institutes across the nation. Dr. Lee is from another one, Nimble, which is dedicated to the future of biomanufacturing. This one's one of the newer institutes dedicated towards cybersecurity and manufacturing across all sectors, initially funded by Department of Energy and various matching funds on sectors of interest to not just future jobs, but also a global impact in terms of energy and emissions efficiency. And that's a very dominant DOE theme. However, there are some more recent engagements with partnerships with Charles, with National Resilience and Nimble itself, where we hope to use some of the things that we're developing and learning and over time to be able to apply and extend into the biomanufacturing sector, which is unique and will require its own innovations. There are significant assets to be brought to bear. And since manufacturing is a inherently cross-pollinated sector, some of the things, particularly on transportation and delivery, are intertwined with the delivery of the production of different biopharma outputs. So the manufacturing sector, when you look at the biggest sectors are getting attacked after financial theft, if you will, from banks and credit card, but the actual control systems and delivery sectors of various physical functions, the power grid and manufacturing sector are always some of the top ones. And one of the long-term challenges that we have is that this sector and IT sectors in general have been driven by a push to market of technologies, as opposed to a secure to market of technologies. And that has some aggregated risks in the end. If you look at the costs in order to fix software flaws, cybersecurity or otherwise, as it's pushed towards closer to the end user or to the end nation, it really escalates in terms of orders of magnitude of what it takes to solve this problem after the fact. And unfortunately, we are where we are, but we still have to address some of those fundamentals and do it in a way in which it's pervasive, unobtrusive, resilient, and economical, so that it's almost transparent to the small innovator that he's joining this ecosystem that has some assurances that are validated at scale in order to participate in this ecosystem. So that's the long-term challenge that research institutes are dedicated towards. And this is the framing, if you will, relative to this institute and the cybersecurity challenges. So let's step back and look at, in this example, how the complexity and sophistication of attacks has progressed in control systems, taking sort of the power grid as an example. The well-known attacks in winter of 2015 on Ukraine by Russian elements, in which hundreds of different substations were taken down and were down for many days, servicing many different customers. This attack was very manual. There was a lot of targeting that went into getting into these systems in advance. But once they're there, they actually use the systems and the human interfaces against them and use them almost as designed, but taking control as the operators in order to do these outages manually. And there's a large number of coordinated teams that did this. One of the things that they did do was a sort of a scorched earth policy afterwards, in which they bricked, if you will, the communications devices that were doing serial to fiber conversion. And so they lost ability to automatically control many of those substations and had to operate them manually for, in this case, years, because they were not able to replace those automation systems. There's many power grids, including our own, many sections of it, where it's not possible for us to wield that type of power in a manual fashion, given the margins that we're running. Part of that attack, first attack, they sucked up a lot of information about the configurations on the protective relays. And so they ended up gathering the intellectual property, if you will, on the safety systems unique to that grid. That was then also used in a larger attack in terms of megawatts, in terms of the transmission system that was hit the following winter. Now, in this case, this was a shorter outage, just a few hours. And not so ironically, it was balanced to trip a large amount of transmission, but not enough in order to scram most of the power reactors that would have to gone offline if they took off enormous capacities of transmission. So they did not go into multiple days or weeks worth of outages because the reactors would have had to been then restart in a very slow process. So very targeted in a physical sense of the type of effect they wanted to have without going beyond it. This one was automated. This was not manual. And so as you see the progression of targeting information that you get from those scientific or engineering workstations, the next level was to the safety instrumentation systems, if you will, on a different type of attacks on Middle Eastern oil and gas processing facilities, petrochemical facilities. And these attacks were actually against the safety systems. So these were memory-based attacks in which they could load different software and change different settings. They're actually keeping the plant within safe control parameters. So in these type of plants, there are parallel control systems that are used, if you will, to implement the formula. If you're doing a chemical processing plant in order to produce it at scale, that, that may be intellectual property in a sense, but these were the actual safety systems run in parallel to guarantee that there wasn't different safety events or explosion events should those processes that are being controlled by the production systems be upset. This is useful in an attack scenario if you are trying to disturb the process and not have the safety systems kick in and effectively take that plant out. Again, they hit the engineering workstations, half a dozen of them. Even though there were some keys involved in whether or not you would load the software, so you kind of turn the key to load program versus run, that was marketed as a form of protection that was not necessarily in place. The fact that they were in the engineering workstations kind of makes that key sequence mute. As soon as they load new software, those engineering workstations are sort of key. And I think there's probably many analogies that you can take, although different systems as you go into different sectors. Some key takeaways besides the importance of these intellectual property stations being used to configure these systems is at the same time they had other objectives relative to influence and information war. But what you're seeing is a strategic targeting of diversity of systems as they progress capabilities and tested on real hardware. At the same time, in similar time frame, the US power grid was penetrated for over 3 years before they were detected, while information was being gathered about the various systems that we operate in, the different control systems that later have some similarities in some cases to where some of these attacks were taking place. So let's relate that now to what's going on in the last couple years. For all practical purposes, cyber attack in a criminal sense is commoditized. You don't have to develop the capability yourself. There's whole suites of services available to you in order to provide you the hacking hardware, the hacking infrastructure, the targeting infrastructure, even the monetization infrastructure, so that your targets can be dialed into, specified, developed against, using existing infrastructure and systems that have various forms of plausible deniability, and then how you monetize it in terms of ransomware and others. And so from a targeting standpoint, you could have some of these assets brought to bear against you, either because you look like a profitable sector because you're as a whole vulnerable, even if your individual facility is not of strategic interest, or you could be targeted in a sense that you are strategic to the US capability or strategic to our economic capability. And for those criminal elements cooperating with nation states, become part of the targeting system. The other thing to note is some recent supply chain attacks on software, hitting administrative software in the actual build process. These are fairly security adept vendors, if you will. I won't comment on the specific access vectors or their adeptness in this particular attack, but in general, these are experts in their field. And we're dealing with sectors that don't have these same level of capabilities at the same time as we have over 120 countries with various forms of different offensive capabilities under development. So when you turn to manufacturing, the simultaneous move of these digital threads, where we are linking the design cycle, whether it's a CNC machine with CAD software or biological protein printing machines with design software based off of DNA sequencing and trying to build the protein and lipid structures that you're looking for. This is happening at the same time as we're not necessarily coming up with a coherent architecture or security mechanisms or consistent protocols to address the fact that the database control is being exchanged, in a more worldwide orchestration of the supply chain, and we're dealing with, in many cases, older systems and a complexity of protocols. So part of the challenges that we're working on as an institute is that we have to move away from this patchwork of protocols and perimeter defenses and more to integrity checks and security properties that have the context of whatever physical, or in this case, biological process that we're dealing with, and enforce those security properties that we need to see across that digital thread between the design lifecycle, the manufacturing lifecycle, and the various analytic life cycles in terms of quality control, distribution, and links to other manufacturing systems. The final slide I'll have is a call to arms, if you will, from the Cyberspace Solarian Commission. And it effectively uses the words that I started out with, is that we now have enough aggregated risk in many of these sectors that has historically been pushed on to the individual company or the individual sector or the individual country that is not going to be tolerable for much longer. And so we have to move to a secure to market rather than first to market. And the only way to do that and preserve the agile innovation is to start putting these tools and thoughtful approaches and frameworks in place in advance so that the innovators are enabled with a DevSecOps or agile-like ecosystem that is relevant to their biosecurity or their specific manufacturing system. And so that kind of concludes my remarks, and I expect that Charles will close with some other more relevant biosecurity remarks.